Good evening, everyone. So we'll be starting today. We'll be discussing today about the cells and the combination of the cells as well. Before starting the series and the parallel combination of cells or discussing about the cells or EMF of a cell, we'll be just discussing some of the questions of the previous lectures that we discussed. So let's start with this question here in the screen. So you can see here on the screen that there is a combination of resistors like a ladder of resistors given in this circuit, right? So to be connected between C and D so that the resistance of the entire circuit between A and B does not change with the number of elementary sets used is. So it means that we have to just find the equivalent resistance about this A and B, right? So these are the ladder of resistors here. You can see here. So these are the ladder of resistors, right? So it's actually an infinite ladder of resistors, right? So it goes up to infinity, right? It's an infinite resistors here, right? Infinite resistors. So what we have to do here in this question is that we have to just find the equivalent resistance for this circuit, right? So what we'll be doing here in this circuit is that let's suppose that since this is an infinite circuit, so we can equivalently redraw this circuit like this, right? Redraw this circuit like this. So this is our R here, right? This is our R, and this is another resistor here, right? And this is the resistor R here, right? We can just do one thing, right? We can just replace this whole circuit with this equivalent circuit, right? We can just replace this portion of the circuit with the R equivalent, right? If we replace this whole portion of the circuit with the R equivalent, right? We can just write here as R equivalent, right? And the resistance of this whole circuit will not change because we have just placed this whole circuit with the R equivalent here, right? And let's suppose this is the R here and this is R here, right? And this is R here, right? So, so the whatever the equivalent resistance will be there between A and B, right? That will be also equal to the R equivalent, right? That will be also equal to the equivalent circuit, equivalent resistance of this circuit, right? So we can see there here we have three resistors here, R equivalent, R. These three resistors, these are in parallel, right? These are in series, R equivalent and R in series, right? We can just redraw this circuit as like this. So this is our R here. So it will be equivalent of this, right? The equivalent of this will be nothing. It will be 2R plus R equivalent, right? 2R plus R equivalent. And we have R here, right? So we can just write down the equivalent resistance for this circuit like this. We can see R and this resistor, now they are parallel to each other, right? So it means their R equivalent will be nothing. It will be equal to R multiplied by 2R plus R equivalent, right? Upon, it will be 3R, 3R plus R equivalent, right? 3R plus R equivalent. And that has to be equal to the R equivalent, right? So this is the equivalent circuit, right? So it means that we have to just find that value of R equivalent here such that the value of the resistance, the value of the equivalent resistance does not change, right? So it means that if we substitute, we can just cross multiply these things, right? It will be 3 times R into R equivalent, right? Plus R equivalent square, right? That will be equal to 2R square plus R multiplied by R equivalent, right? So if we rearrange this circuit once again, so we will have this equation R equivalent square. It will be equal to plus twice R into R equivalent, right? Minus 2R square, right? That will be equal to 0, right? And you can see that in the form of R equivalent, it's a quadratic equation, right? It's a quadratic equation, right? We can solve this using the uh, quadratic formula, right? So it means from here the R equivalent will be nothing. That will be equal to, that will be the minus B. So the minus B here is minus 2R, right? Minus 2R plus minus under root of P square minus 4AC, right? That's the discriminant of this equation, right? B square is nothing. It's 2R square. That will be 4R square minus 4AC. So it will be minus 4 into A. The coefficient of R equivalent square here is 1. So we'll multiply it here with 1. And C, the value of C here is nothing. It's 2R square, right? It is 2R square, right? So upon, it is 2R square, right? Coefficient of, sorry, it's minus 2R square, right? C, the value of C is minus 2R square. So we'll just write here as minus 2R square upon 2A. And the value of A here is once again 1. That will be 1, right? So from here, it means that our R equivalent will be nothing. It will be minus 2R plus minus. So it will be 4 to the 8 and minus minus it will be plus, right? So it will be 12R square. We can just get this R outside. So 12 under root of 12, we can write it as 2 root 3, right? It will be 2 root 3. 2 root 3, right? Upon 2. So from here 2 and 2, this will get cancelled. We'll be left with minus 2R. We'll be left with minus 2R plus 2 root 3 R. Sorry, it will be minus R plus root 3R, right? Minus R plus root 3R. Minus R plus root 3R, right? This will be the equivalent resistance, right? It means that if we take the another root, that negative root, it means that the overall resistance will become negative, and the resistance cannot be negative. So we'll not be taking the another root of this equation, right? Because it will not be a physically acceptable solution for this R equivalent, because resistance of a conductor cannot be a negative resistance, right? So that's the reason you can see that root 3R is greater than minus R, right? If root 3R is greater than minus R, it means overall the resistance is a positive here, right? So we'll be taking only the positive resistances. We'll not be taking the negative resistance here. That's why we choose only the plus solution here, not the negative solution here. So finally, the value of R equivalent comes out to be, so the R equivalent will be nothing. It will be root 3 minus 1 multiplied by R. So this will be the final equivalent resistance for this circuit, right? It's a ladder infinite circuit. So this is how we can find the equivalent resistance for this ladder type circuits, right? And similarly, in case of capacitors, if we have infinite ladder of capacitors, right? So we can also find the equivalent capacitances in the same fashion, right? In the same fashion for infinite capacitors, right? Let's move on to the next question now. So the question here is a battery of EMF 10 volt. You can see here in this circuit, there's a battery of 10 volts connected to resistance as shown in figure, right? The potential difference VA and VB, right? We have to find the potential difference between the 2 points we can see here in the circuit. We have 2 points here, VA and VB. We have to find the potential differences between these 2 points, A and B, right? So what we can do is that, let's suppose that if we find the equivalent circuit for this equivalent resistance for this circuit, right? If we find the equivalent resistance for this circuit, you can see that these two resistors, 1 ohm and 3 ohm, these two resistors are in series. So we'll have the equivalent resistance for these two resistors as 4 ohm, right? And similarly for 3 ohm and 1 ohm, we have equivalent resistance as 4 ohm, right? And now then these 4 ohm and 4 ohm resistors, these two resistors will be in parallel to each other, right? If these 4 ohm and these two 4 ohm resistors will be parallel to each other, the equivalent will be nothing. It will be 4 into 4 upon 8, right? So it will be 2 ohm, right? It will be 2 ohm. So it means that we can just replace this whole circuit, this whole circuit can be just replaced with the equivalent of 2 ohm resistor, right? Which means that we can redraw this circuit like this. We can redraw this circuit like this. So this is 3 ohm, this is 2 ohm, right? And we have this battery of 10 volts, right? We have this battery of 10 volts, correct? So this is the battery of 10 volts. And now finally, if I is the current, right? If I is the current, so this I current drawn through the battery will be nothing. It will be the potential difference across the battery, right? That's 10 volt, and the total resistance. And you can see these two resistors, 3 ohm and 2 ohm resistors, are in series with each other. So it will be 3 plus 2, that's 5. It means that the battery will be drawing a current of 2 amperes, right? The battery will be drawing a current of 2 amperes through this circuit, right? So it means that this will be the direction of the current. 2 amperes current will be through this circuit, right? 2 amperes current will be through this circuit, right? So if this 2 amperes current will be through this circuit, now at this point, now this is the junction point, right? Now at this point of junction, the current will be now distributed along two branches. There is a branch along A and there's a branch along B, right? And you can see that both these branches are identical. If the two branches are identical, then the current will be distributed equally between the two branches, right? So it means if the total current here is coming out to be 2 amperes, then 1 ampere will flow through this branch and 1 ampere is going to flow through this branch, right? So this is how the current distribution will be in this circuit, right? But we have to find the potential difference between points A and B, right? Let's suppose that we choose this point here. Let me call this point as C, right? Let me call this point as C, right? And if this is the point C, right? Point C, uh, and the current is flowing through this 1 ohm resistor, right? Current is flowing through this 1 ohm resistor. It means that the potential difference across this 1 ohm resistor will be nothing. The potential at point C, that's VC, and the potential at A, that's VA, that's VC minus VA. It should be equal to the current flowing through this 1 ohm resistor, that's 1 ampere, multiplied the resistance of that 1 ohm resistor, that's 1 ohm. It means that it should be equal to 1, right? Similarly, for the 3 ohm resistor here, the current is flowing 1 ampere, and VC minus VB will be equal to, that's IR. I is 1 ampere and the resistance is 3. That will be equal to 3, right? That will be equal to 3. So let me call this as equation first, right? And let's suppose this is equation second. Now subtracting the equation second, right? Or the equation first, uh, subtracting equation first from second, right? So what we'll be doing is that VC minus VB, right? It will be minus VC plus VA, right? That will be equal to 3 minus 1, right? That's equal to 2, right? Now this VC plus VC and minus VC will get cancelled out. We're left with nothing. That's VA minus VB, right? That's equal to 2 volts, right? It means the potential difference between these 2 points, VA and VB, is nothing. It's equal to 2 volts, right? So that's how we solve this problem, right? Using the concept of equivalent circuits, right? And the concept of current distribution here at this point C, right? So 2 volt is the potential difference between V and VB, right? So let's move on to the next question here. You can see here in this circuit we have uh, two resistors here, 28 ohm and 54 ohm, right, in this circuit, right? So the question is that we have to find this current I3, right, in this circuit. The current I3 that's flowing through this battery of 6 volts, right? We have two more batteries here. One is 8-volt battery, another is 12-volt battery, and we have two resistors, 28 ohm resistor and the 54 ohm resistor, right? So in order to find this current I3, we will be using Kirchhoff's voltage law, right? If we use the Kirchhoff's voltage law, right, KVL here in this circuit, right? So what we'll be doing is that, let's suppose that the current I1 is coming here, right, at this junction, right? Current I1 is coming at this junction, and let's suppose that out of this current I1, I3 current flows through this point, right? And then the current left is nothing. Let's that current will be nothing. It will be I1 minus I3, right? I1 minus I3, right? That will be the current flowing through this circuit, right? Let me call this mesh 1, right, loop 1, and let me call this as loop 2. So in loop 2 the current flowing will be I1 minus I3, and in loop 1 the current will be I1, and through battery 6 volt the current will be I3, right? So this is how the current has been distributed in this circuit of two loops, right? In the circuit of two loops. So what we'll be doing is that we'll be just applying the KVL in the loop 1, right? Applying KVL in loop 1, applying KVL in loop 1. By default, we can just choose this direction, right? You can just choose this direction, both the loops, right? Clockwise direction, right? You can choose any directions you wish, right? But I'm choosing here a clockwise direction, right? So, so it means that applying the KVL in this loop 1, right? So here in this loop, you can see that if I start from this point, right, in this loop, then I will be first facing the positive terminal of this 8-volt battery. I will be first facing the positive terminal of this 8-volt battery. So I'll be taking this EMF of this battery as a positive plus 8, right? Plus 8. And then the current in 28 ohm is given as I1, that's I1 amperes, right? And I'm moving along the direction of this current I1 here. So I'll be taking the potential drop here as positive, that's 28 I1, right? 28 I1. Now facing the I will come in this direction, in the downward direction. I will once again face the positive terminal of this 6-volt battery. So I'll be taking it as +6, right? I'll be taking it as +6, right? +6, that will be equal to 0, right? Let me take it as +6, that will be equal to 0, correct? So this is our equation first. So I can just simplify it again. So it will be 20, or we can write it as 14I1, right? 14I1, that will be equal to, right? 14I1, that's 14I1, right? Plus 14, right? That will be equal to 0, right? That will be equal to 0, correct? So 14I1, sorry, it will be 28I1 plus 14, right? 28I1. 28I1 plus 14, that's equal to 0, right? So it means that now applying the KVL in the second equation, right? Applying the KVL in the second loop, right? Applying KVL in loop second. Applying KVL in loop 2, right? Once again, we'll be moving in the same fashion, right? We'll be moving in the clockwise direction. And let's suppose if we start from this point here, right? If we start from this point D here, right? We'll be facing the negative terminal of this battery 12 volt. We'll just write it as -12. And now we'll be facing the negative terminal of the 6-volt battery. We'll be writing it as -6. And then we'll be left with, we'll be now moving along the direction of the current. In case of 54 ohm resistor, we'll just take it as positive. That's 54 I1 minus I3, right? That's equal to 0, right? That will be equal to 0, right? Let's rearrange it. So it will be 54 I1 minus 54 I3, right? Minus 18. That will be equal to 0, right? That will be equal to 0. So we can just cancel out it here. So it will be 18, 1, 3, right? So it will be once again 3. So it means 3 times I1 minus 3 times I3, that has to be equal to 1, right? That has to be equal to 1. Now we have two equations here. This is the equation and this is the another equation. From here, if we calculate the value of I1, the value of I1 will be nothing. It will be equal to minus 14 over 28, right? That will be equal to minus 1 upon 2, right? Minus 1 upon 2. We'll just substitute the value of I1 here as minus 1 upon 2. It will be minus 3 upon 2, right? Minus 3 times I3. That's equal to 1, right? Or our I3 will be having a value of, it will be 5 upon 2, right? 5 upon 2, right? It will be 5 upon 2 upon minus times 1 upon 3, right? That will be equal to minus 5 upon 12 amperes, right? So I3, so it means that minus 5 upon 12, it means that current cannot be negative, but it actually tells us about the direction of the chosen current, right? It means that if the direction of the chosen current is along this direction, it means actually it's flowing in the opposite direction, right? So if we talk about the magnitude part only, the current I3 will be nothing. It has to be equal to 5 upon 12 amperes, right? So that's it. So current cannot be negative, but if there is a negative current, it means that the chosen direction by default was incorrect direction, and the actual direction of the flow of current is opposite to that direction, right? So that's it. That's what the negative sign of this current signifies here, right? So 5 or 12 will be the current flowing through this battery of 6 volt. So that was it for, with respect to the previous lectures, and these were some of the questions related to the KVL, right? Let's move on to the next topic, very important topic, right? The topic is EMF of a battery, right? We'll be discussing now cells, right? Particularly the EMF of a cell, right? Potential difference and the terminal voltage. What is all these terms signifies, right? So we'll be starting with the electromotive force, that's EMF of a cell, right? So EMF of a cell is nothing. It's the maximum. It's nothing. It's the maximum potential drop across the terminals of a battery, right? It's the maximum potential drop across the terminals of a battery, right? So let's suppose these are the two terminals of a battery here, right? These are two terminals of the battery A and B, right? When no current is drawn through this element, right? And no current is drawn in the circuit, then the EMF or the potential drop across the two ends of this battery is what we call as EMF, right? EMF is nothing, it's the maximum potential drop, it's the maximum potential drop, PD, right, across the terminals of a battery, across the terminals of a battery, terminals of a battery when no current is drawn, when no current is drawn, right? So the maximum potential drop across the terminals of a battery when no current is drawn, that's what we call as EMF of a battery, right? When no current is actually drawn. So that's what we call as EMF of a battery, right? That's what we call as EMF of a battery when no current is drawn, right? So it means that here in this case, actually the current I drawn is equal to zero. Then we can say that then the maximum potential drop uh, across these two ends of a battery will be nothing. That will be E. That is what we call as EMF, right? EMF, right? Now, one more important point about this: once the current is drawn through the battery, then the important thing that comes into the play is that's the internal resistance of a battery, right? Battery has also got resistance, right? Ideally, we were speaking that we were not considering the resistance offered by the battery when current flows through the battery or in a circuit, right? But that's the ideal situation. But actually what happens is that there is always some resistance offered by the battery as well, right, during the flow of current, right? So then we define the internal resistance of a battery. That's what we call as the internal resistance of battery. It's the resistance offered by the electrolyte of the cell. We know that any electric cell consists of electrolyte in it, right? It's made up of some electrolytes, right? And the resistance offered by those electrolytes for the current to flow through it, through the battery, right? That's what contributes to the resistance or the internal resistance of a battery, right? So whenever current is flowing through the battery, then battery also offers some resistance to the flow of current, right? That that resistance we call as internal resistance of a battery, right? So that's the internal resistance of battery. So we have two things here. One is the EMF of a cell, and another is the internal resistance of a battery. Now, in cases where there is no mention of the internal resistance of battery, we'll just by default take the internal resistance of a battery to be equal to zero. It means that we'll be considering the ideal case in that situation, right? But in most of the times, or in some cases, there will be given a resistance of a battery as well. Then we have to consider that internal resistance of battery for the calculation of any physical quantity, be it current, be it potential difference in a circuit, right? So then we'll be taking the internal resistance of a battery into consideration as well, right? So let's move on to the next concept. That's about the terminal potential difference, right? Now the question is that we define the EMF of battery or the electromotive force of a battery. That's nothing when this is the maximum potential difference across the ends of a battery, right? Across the ends of a battery when there is no current drawn, right? When there is no current drawn. But the question is that what happens when the current is drawn in the circuit, taking into consideration the internal resistance of a battery as well, right? In that case, what happens is that in that case, there will be some potential drop across the internal resistance of a battery. So what we have done in this circuit, you can just look at it, look at this circuit. This is the external resistor, right? This is the external resistance, right? This is the external resistance. This is the external resistance, right? Or we call it as load, right? Or load, right? Now this small r is nothing, it's the internal resistance of a battery, right? This is nothing, this is the internal resistance of a battery. This is the internal resistance of battery, right? Or cell, right? This is the internal resistance of a battery, right? So the EMF of this battery is E. So this is the maximum potential difference when there is no current flowing through the circuit. But the question is that now when the current flows through the circuit, then across these two ends, right? These two ends, right? These two ends, what will be the potential drop, right? And that potential drop across these two ends when the current starts flowing through the circuit, that potential drop we call it as terminal potential difference, right? So terminal potential difference is nothing when the current flows through the circuit and we are considering the internal resistance of a battery as well. Then in that case, there will be some potential drop across the internal resistance of a battery as well. So in that case, there will be a different potential difference across the external load, or we can say there will be a different potential difference across the two ends of a battery, right? In that case, we call that potential difference as what we call as terminal potential difference, right? So we can say that we can rewrite it as like this. So let's suppose the current I is flowing through the battery, right? Current I has started to flow through the battery, right? So if I is the current, right, then there will be some potential drop across this what we call as internal resistance, right? Then E will be nothing. Some potential drop will be. We can just use KVL also, right? If we use the KVL in this circuit, right? If we use the KVL in this circuit, like let's suppose we are using the KVL, right? Using KVL, using KVL in this circuit, right? If we use KVL in this circuit, right? So we are moving here in this in the anti-clockwise direction, right? If we are going in the anti-clockwise direction, it means that we'll be facing the negative terminal of this battery, right? It will take the EMF as minus E, right? And for this resistance R and capital R will be moving along the direction of the current. So we'll be taking it as IR and plus I into capital R, right? That should be equal to 0. So this is the KVL, right? This is the KVL. So it means that from here, so our I into R plus IR, that will be equal to E, right? That will be equal to E. Now this I into R, this I into R, that's equal to V. What is this I into R? This is nothing. This is the potential difference across the ends of this resistor, this load R, right? This is the potential difference across this load R. That's equal to V, right? That's equal to V. And same is the potential difference across the two ends of this battery. It means that this V is nothing, is the terminal voltage, right? It's the terminal voltage. This V, what we call as terminal voltage. So this V is nothing. This is a terminal voltage, right? So it means that we can just replace this IR with V. So it means that V is nothing. Terminal voltage is nothing. It's E minus IR, right? E minus IR. So this is what we call as the terminal voltage of a battery, right? So this is nothing. This is the terminal voltage of a battery. So we can say that VT, that's the terminal voltage of a battery when the current flows through the circuit. It's nothing. It's the EMF of a battery minus the I times, that's the current, times the internal resistance of a battery, right? So it means that when the current flows through the battery, when the current is discharging, or the we can say the battery is discharging, right? In that case, the terminal potential difference is less than the EMF of a battery, right? So this was with respect to the terminal potential difference of a battery. This is how we understand the terminal potential difference of a battery. Now the question is that uh, there are two cases, two situations. The situation one is that when the battery is actually, situation one is that when the battery is discharging, right? And another situation is that when the cell is getting discharged, when the cell is getting actually charged, right? Discharging and the charging cases, right? Let's discuss first case, that is when the cell is actually discharging, right? So you can see that when the cell is actually discharging, then the current will be flowing from the positive terminal of the battery and will end on the negative terminal of the battery, right? So this is how the direction of current will be when the uh, cell is actually discharging from the circuit, right? So what we can do here is that we can just apply the KVL in this situation as well, right? Then in that case, V will be the potential difference across the ends of the battery. Let me call this potential difference across the ends of a battery as V, right? We also found that this V is nothing, it's E minus IR, right? We can just apply the KVL again, right? KVL again in this circuit, right? If we apply the KVL in this circuit again, that will be minus E, right? Plus, since we are moving in the direction of the current flowing, so we'll just take it as plus IR and plus I times capital R. That will be equal to 0, right? So from here, and this IR is nothing. This is the terminal voltage, that's VT, right? So we can just write this terminal voltage as VT, that's E minus IR, right? E minus IR, right? Or if we have to find this current I will be nothing. It will be the total EMF, that's E, upon the total resistance, that's R plus R, right? This will be the current flowing through the circuit, right? This will be the current flowing through the circuit, or current flowing through this system when the battery is actually discharging, right? So you can see here in this case, the terminal voltage when the battery is actually discharging, it's actually less than the EMF of a battery, right? It's actually less than the EMF of a battery. Why? Because there is always some potential drop across the internal resistance of a battery as well. That's the reason. That's the reason. The terminal voltage is actually less than the EMF of a cell. So when the internal resistance of a battery comes into play, right? Practically there is always some resistance offered by the battery, but ideally speaking there will be no resistance offered by the battery. In that case the terminal voltage will be the same as the EMF of a battery, right? Now, the case second is here when cell is getting charged, right? And when cell is getting charged, it means now the current will be flowing in the opposite direction, right? The current will be now flowing opposite direction. It means current will be now flowing from negative terminal of the battery to the positive terminal of this battery, right? It will be now getting charged, right? It will be now getting charged, right? Now let's apply the KVL in this case also, right? If it is getting charged, we can just see that this is the V is now the terminal voltage. Now applying the KVL in this case also, right? Let's apply the KVL in this case also, right? Now here the EMF, we are facing the positive terminal of this battery, that's plus E, right? And we are once again moving along the same direction of this, along the same direction of what we call as this current I along the internal resistance of the battery. We'll just write it as plus IR, right? Plus IR, and we'll be facing the negative terminal of this terminal voltage, negative terminal of this terminal voltage. We can write it as minus V, that will be equal to 0, right? That will be equal to 0. It means that this terminal voltage V T now in this case is nothing. It's EMF plus IR, right? EMF plus IR. It means now here in this case, the terminal voltage is actually greater than the EMF of a cell, right? So when the battery is actually charging, right, and when the battery is discharging, right, there are two cases. Case number one is that when the battery is discharging, the EMF of a battery is greater than the terminal voltage, right? When the cell is actually getting charged, then in that case, the terminal voltage is actually greater than the EMF of a battery, right? So it's not always that EMF will be less greater than the terminal voltage. It depends upon the case, whether the battery is discharging or the battery is charging, right? So let's discuss about the third case as well when the cell is in open circuit, right? We just defined that the current is actually nothing. It's equal to epsilon upon R plus R, right? In that case, when the cell is in the open circuit, right? When the cell is in the open circuit, right? In the open circuit, there will be no current flowing, right? The current will only flow when there is a circuit is closed. If the circuit is open, then the current flowing through the circuit will be equal to 0, right? In that case also, in that case we know that the terminal potential difference across the battery will be nothing. It will be the EMF of a battery. So we can say that in that case terminal potential difference is nothing. It's equal to the EMF of a battery, right? So in that case the terminal potential difference will be the same as the EMF of a battery, right? So that was about the EMF of a cell, right? That was about the EMF of a cell, right? Now today we'll move on to the different combinations of a cell, right? We can sometimes place cells in series, we can sometimes place cells in parallel, or we can sometimes place cells in both the combinations, in the mixed combination with different polarities, right? Let's start with the combination of cells in series, and then we'll be discussing the cells in parallel as well, right? So you can see here in the same fashion now the cells are in series, right? The cells are in series. It means that their internal resistances will have the same current flowing through them, right? That's how we say that now the cells are in series, right? Because the current, whatever be the current, you can see here that the current actually flowing is I, and the same current is flowing through the internal resistances of this battery, right? So R1, R2, R3, and R4 up to Rn, these are nothing. These are the internal resistances of each of the battery or each of the cells here, right? So the equivalent circuit for this system we can just draw like this. We have some equivalent EMF offered by this circuit, right? By this series combination of the cells, and the equivalent resistance will be given as R equivalent, right? So upon the external load, that's R, right? So it means that these are in series, right? If these are in series, it means that we can just apply the KVL here in this case also, right? If we apply the KVL here in this case also, let's suppose if this is the current flowing, if we apply the KVL in this direction, right? If we apply the KVL in this direction, right? Then we can write this KVL equation like this, right? KVL equation will be like this. We'll be facing negative terminals of all this battery, right? So you can see here the polarity of the batteries, even E2, E3 or cells are in the same fashion, right? There is no opposite polarity. The polarity is in the same fashion, right? It means that if we apply the KVL in this circuit or in this loop also, so what we'll be having is that will be facing the negative terminal of this battery. It will be minus E1, minus E2, minus E3, right? Minus E3, and minus so on up to En, right? Up to En, right? And plus will be having the equivalent resistances, or we can say we will be having the current flowing through these internal resistances. That will be I, right? Will be moving in the same direction as the direction of the current. So it will be I times R1 plus R2 plus up to so on up to Rn, and finally there will be the uh, external resistance, that's the load resistance, right? That will be R, that will be equal to 0. So that's how we can apply the KVL for this series combination of the cells, right? So the equivalent resistance, we can see that the current is nothing, the current here in this case will be nothing, the current will be nothing, it will be E1 plus E2 plus E3 up to so on, right? Up to En, so right, up to En, so divided by R1 plus R2, right? So on up to Rn plus this external resistance load, that's R, right? That's R. That means that it means that we have current equal to the sum of the each and every EMF of these cells, right? Algebraic sum of all the EMFs of the cell when they are placed in same polarities, right? In the same fashion, right? Upon the equivalent resistance. So it means that we can just replace this E equivalent with E equivalent will be nothing. It will be summation of E, right? En, where n runs from 1 to n, right? And similarly, our R equivalent will be nothing. R equivalent will be nothing. It will be the summation of internal resistances from n equal to 1 to n plus this resistance R, right? So this is how we can find the equivalent resistance and the equivalent EMF of a battery, right? So the equivalent EMF of a battery is nothing. It's just the sum of all the EMFs, right? We can just write here the equivalent EMF is nothing. It's nothing in case of series combination. That's E1 plus E2 plus E3, right? Up to so on up to En, right? And similarly, R equivalent is nothing. That's equal to R1 plus R2 plus R3, right? Up to so on Rn, right? So this is the equivalent resistance of battery in case of series combination of cells, right? So let's discuss two cases here, right? The case number one here is when the cell actually support each other. And what do you mean with the cell actually support each other or cell does not support each other, right? We can see here we have two cells, right? We can see here we have the polarity here is plus and here is minus, but here in this case the polarity is once again in the same fashion, that's plus and minus, right? And there is some current flowing through the circuit, right? There is some current flowing through the circuit. So for this combination, we call these two combinations this fashion of the cells, placing the cells in a circuit, we can see that the total EMF, E equivalent EMF is nothing. The equivalent EMF is nothing. That's E1 plus E2, right? Or we can say in this case the R equivalent is nothing. That will be equal to uh, R equivalent will be nothing. That will be equal to R1 plus R2. These are the equivalent internal resistance of these two batteries plus the external resistance, that's R, right? So it means that the total EMF is actually getting add up, right? So we are adding the two EMFs here, right? Because they are having the same polarity, right? They are having the same polarity. So if they are having the same polarity in this case, that's why we say that the two cells support each other, right? The two cells support each other. It means that in this case the current I will be nothing. That will be equal to E1 plus E2, right? Upon R1 plus R2 plus this capital R, right? This will be the current flowing through this circuit, right? Now, what we are doing in the second case is that in the second case, we are doing one thing, that is, in the second case, we are just reversing the polarity of these cells, right? Here the polarity was from plus minus. Now, in this case, it's from minus to plus. So we have just reversed the polarity, right? If we apply the KVL once again in this equation, in this case also, right? Let's apply the KVL in this equation, in this circuit also, or in this loop also, right? So applying the KVL, it will be nothing. We'll be having plus E2, right? Plus E2 here, right? Minus E1 here, right? Minus E1 here, right? And we'll be having the plus I times R1 plus R2 plus R, right? That has to be equal to 0, right? Or from here, we can just see that the current I is nothing. current I is nothing, right? The current I is nothing. It's equal to actually E1 minus E2 upon R1 plus R2 plus R, right? So you can see that the two EMFs or the two cells here are not supporting each other. They're actually opposing each other, right? They're opposing each other. So that's why we say that here in this case, the current will be less. Here in this case, the current will be more, because in this case, the two EMFs are supporting each other. But in these two cases, the two EMFs are not supporting each other. They are with opposite polarity, right? So that's why we say here the current is E1 plus E2. Here the current will be E1 minus E2 upon R equivalent, right? So that's the total current. That's the two cases here when the two cells actually support each other and the two cells oppose each other, right? So let's try to discuss or try to solve this question here on the screen, right? The question here is that we have to find the readings of voltmeters V1 and V2, right? We have given two cells here, each of potential difference or EMF 15 volt and 10 volt, right? 15 volt and 10 volt are the EMF of these two batteries, right? And there is some current flowing through this circuit that's equal to I. And we have the internal resistances of these two batteries as 1 ohm and 1 ohm each, and there is some external load or resistor here that's equal to R is equal to 3 ohm, right? So you can see here, we can just apply the KVL here in this situation as well, right? If we apply the KVL, we'll come to know about the current flowing through the circuit, right? It's your choice in which direction you want to apply the KVL here in this circuit, right? Let me apply the KVL in the anti-clockwise direction, right? So it's completely your choice in which direction you want to apply, right? So I'm applying here the KVL in the anti-clockwise direction, right? Or we are if we are applying the in the anti-clockwise direction, it means that I will be facing the negative terminal of this 10 volt battery. We'll just write it as minus 10 volt, and I'll be facing the positive terminal of this 15 volt battery. I will just write it as 15 volt, right? Plus 15 volt. Now I'm moving along the direction of the current flowing through all these three resistors, right? 1 ohm, 1 ohm, and 3 ohm, right? So it means that I can just write here is I multiplied by 1 plus 1 plus 3. That's equal to 0, right? That's equal to 0. So it means that it will be 5 plus I times, uh, so it will be 15 minus 10, that will be equal to 5, right? And 3 plus 2, that will be 5, right? That will be equal to 0, right? It means the current I is actually in that case, it's equal to 1 amperes, right? It will be equal to 1 ampere, right? So whatever with the direction, so actually it will be a minus 1 ampere, right? Let's recheck it whether we applied KVL correctly or not, right? We have chosen this to be the direction of the current, right? And this is the 3 ohm, right? It will be equal to 3i, right? Plus 3i, and it will be equal to here plus 2i, that will be 5i, right? And this is the minus 10, right? And plus 15, right? That's correct. It means that actually that if this is the given direction of the current, but we are getting minus 1 ampere, right? It means that actually the current is not flowing in this direction. The current is actually flowing in the reverse direction, right? This is the current. This is how the current actually flows, right? Now, uh, we have to calculate the terminal V1 and V2 measured by this voltmeter, right? Measured by this voltmeter. It means V1 and V2 are nothing. These are the terminal potential drops, per terminal potential drops across the two batteries. That's 10 volt and the 15 volt, right? It means that if 1 ampere of the current is flowing, it means that we will have the potential drop across this resistor as equal to 1 volt, and we will have the potential drop across this internal resistor equal to 1 volt as well, right? We'll have potential drop equal to 1 volt, right? So it means that the potential drop across, we have to find the value V1 and V1 and V2, right? So 15 volt is the total potential drop, right? 15 volt is the total potential drop, right? So it means that the term V1 will be measured, so it will be 15 minus 1. That will be equal to 14 volts, right? So V1 will be measuring 14 volts of potential drop, and V2 will be measuring the potential drop of 9 volts, right? So 9 volts will be the potential drop measured by V2, and the 14 volt will be the potential drop measured by V1, right? So that's the measurement of these two voltmeters, right? In this case. So let's move on to the next question here also, right? The question is that once again the same question, that in the circuit you can see that we have just placed these two resistors or this battery in this triangular form, right? We can just rewrite this equation, rewrite this circuit in this form as well, right? We have to find the reading of this voltmeter, right? We have to find the reading of this voltmeter, right? And let's suppose this voltmeter is ideal voltmeter, right? This is an ideal voltmeter, right? Ideal voltmeter. It means that if the voltmeter is ideal, it means that there will be no current flowing through the voltmeter itself, right? Ideal voltmeter means that we have a voltmeter of actually infinite resistance. If there is infinite resistance of this voltmeter, then it will not actually contribute to the current, right? There will be no current flowing through this voltmeter, and this voltmeter is always connected along in a parallel, right? And there will be no current flowing through that voltmeter, and it will be measuring the potential drop across the two ends with great accuracy, right? So so here in the fashion, the way the voltmeter here has been connected, it means this voltmeter is going to measure the potential drops across the two terminals of this battery, right? Two terminals of this battery. If this is going to measure the potential drop across these two terminals of the battery, it means that it's going to measure the terminal potential difference, right? So let's do one thing. Let's apply the KVL in this circuit as well. Let's try to find the current in the circuit, and then we'll be able to find the measurement done by this voltmeter, right? So it is actually given that we can just find that 1/5 ampere is actually flowing through this circuit, right? Uh, if we apply the KVL in this equation, right? So we'll have minus 10 volts, right? Plus 4 volts, right? Plus I times 30, right? That will be equal to 0, right? We have just applied the KVL in this circuit, right? So it will be minus 6, that will be equal to minus 30i, right? Right, 30i. So I will be nothing, it will be 6 upon 30. 6 upon 30, that's nothing, that's equal to 1/5 amperes, right? So 1/5 amperes is the, or we can say 0.2 amperes is the current flowing through this circuit, right? If 0.2 amperes, not 0.5, it's equal to 0.2 amperes, right? 0.2 amperes current is flowing through this circuit, right? It means the potential drop across this 10 ohm resistor then will be equal to nothing. It will be 10 multiplied by the 1/5, that will be equal to 2 volts, right? That will be equal to 2 volts, right? If this is the potential drop across this 10 ohm resistor, and 10 volt is the battery EMF of this battery, it means that this voltmeter is actually going to measure the potential drop of 10 minus 2. That's the terminal potential drop, that will be equal to 8 volts, right? The measurement of this uh, voltmeter in the circuit will be nothing, it will be equal to 8 volts. So it will be measuring a potential drop or the terminal potential drop of 8 volts, right? So that's it for today, right? We'll have to stop today here, right? So in the next lecture, we'll be discussing about the parallel combination of the resistors as well, right? Parallel combination of the cells in the next lecture, right? So till then, take care and goodbye.